All right, and so let's go ahead. I want to do a practice problem because I know that this math is getting kind of weirder and weirder. So here's our problem set. Okay, it says Dr. Bobbitt does not always let his statistics class out when the bell rings. In fact, he seems to end class according to his own quote unquote internal clock. This internal clock will go off anywhere between 1 minute before the bell rings to 4 minutes after the bell rings. Furthermore, all points in this time span are equally likely. So it's equally likely to let them out 1 minute before the bell rings, right when the bell rings, 5 seconds after the bell rings. All of those different possible outcomes are equally likely. All right, now when I draw the probability distribution for this, is it going to be a bell curve like what we see right here? Is it going to be a bell curve like what we see right here? So I'll go back down so you can see what the problem is. All right, so can I get a hand raise if you think that it will not have a bell curve? All right, so if you put your hand up, then you are correct. Let me try and hear from somebody. I can't really see your faces. Hopefully, at the very least, I can get to recognize your voices. Max, are you there and are you able to talk? All right, thank you, Max. Um, what made you say that we are not going, what made you think that we're not going to have a bell curve for this problem?
Since all points are equally likely, it's just going to be a flat kind of like the rectangle in the.
Yes, perfect. Thank you very much, Max. So yeah, it's gonna be a rectangle. So let me go ahead and put one in there. We'll have a rectangle, and then on the far left end, all right, you might get out 1 minute early, so that'll be -1. All right, 1 minute before the bell, and then on the far right hand end, you're gonna have a +4. All right, meaning that you could get out 4 minutes after the bell rings. So you could get out anywhere from 1 minute before. I'll go ahead and just put 0 right here. All right, or you could get out right here. That's right when the bell does ring. All right, 1 minute after the bell rings, 2, 3, or up to 4 minutes after the bell rings. It's not going to be it's not going to have this bell curve, because remember what this bell curve tells us about heights in this example is that males that are around 71 inches are fairly common, all right, but males that are around 77 inches, their height is a lot lower, so they are a lot less frequent, a lot less common, all right, a lot less likely, you could say. But in our scenario, I'm equally likely to let you out 1 minute before the bell rings, 3 minutes after the bell rings, anywhere in between. All those possibilities are equally likely. All right. So here's our next question. Can I get a hand raise if you know how tall this distribution is going to be?
Wouldn't it be like 1/5?
It's going to be 1/5. And why is it going to be 1/5?
Because there's like 5 different intervals, kind of. If that makes sense.
Well, I know what you're saying. You're saying that there would be like, basically this length right here is going to have a length of 5.
Yes.
All right. So this is going to have a length of 5. Now, why does, because we got 0 to 4, so that's 4 units right here. Then we've got our 5th unit going from 0 to -1. Now, given that our length on the bottom is 5, why is our height going to be 1/5?
Because like each from like -1 to 0 is like 1, and then 0 to 1, they're like
No. I got you there, and
Oh.
you've answered everything right so far. So the height is going to be 1/5, and the reason is because the length is 5. Now, if the length is 5, then why do we have to make the height be 1/5? In other words, what does the area making up this rectangle, what does it have to add up to?
Oh, has to add up to 1.
Right, there we go. All right. So the area making up this distribution has to add up to 1.0, or in other words, to 100%. Okay, so we've got our height, and we know the shape of the distribution. All right, so let me go ahead and drop the question. All right, so what's going to be the probability that you're let out within 1 minute of the bell? What's the probability that you're going to be let out within 1 minute of the bell? All right, and I'll go ahead and say, so basically, what's the probability that you get let out anywhere from here to, we'll say right here, +1? So when you have the answer, go ahead and just put it in the meeting chat for me so I can see how you guys are doing. Okay. I'm kind of in. Are you in this meeting right now too? You're in a different one. All right. Actually, hold on. Let me just mute the mic and then I'll take a quick look at it.
It was just
All right. So I've got 2 people that got it right. I'm gonna ask you guys another one right after this, and I'm hoping the numbers are gonna go up a little bit. So, what's the length of this time frame? All right, going from 1 minute before the bell goes to 1 minute after, that's going to be a 2-minute time frame, so that's our length. And so all we're going to do here is we're going to do our length, which is 2, times our height, which is 1/5. All right, which is, if you were to put that in your calculator, you would get 0.4. All right, so in other words, there's a 40% chance that I let you out within 1 minute of the bell, either between 1 minute before the bell goes off and 1 minute after the bell goes off. And so if I shade in this area, the idea here is, remember I told you that this total area, the area of this entire rectangle, has to be 1, all right? So it's 100% of the area, this whole thing. Now, what percent of that area have I shaded in? 0.4 or 40% of that area, which means that there is a 40% chance that I let you out within 1 minute of the bell ringing. All right, somewhere between 1 minute before the bell rings and after the bell rings, 1 minute after the bell rings. All right, now I'm going to go back and tie this again to height. So I shaded in the area under this curve. Remember, the area under this whole curve, just like what we had down here, it has to ultimately be 1. All right. If you calculate the area under this whole curve, it will add up to 1. Now I've shaded the area between 68.1 inches and 73.6 inches. All right. And we don't know how to get this calculation, okay? We would have to be applying calculus. But what I'm going to say is that if I were to look at what this area is, it would come out to being 0.68. In other words, I've shaded in 68% of this total area, and that means that people with heights between 68.1 and 73.6 inches, they make up 68% of adult males, and so any given adult male also has a 68% chance. So like if you give birth to a male, all right, there's a 68% chance that that child will grow up to be somewhere between 68.1 inches and 73.6 inches. All right, now on the other hand, you know, maybe this part that I'm shading, all right, if I were to look up what that area is equal to, we'll say that that area is equal to 0.05, or yeah, we'll just say 0.05, make it simple, all right? So that means that there is a 5% chance that that child will grow up to be 65.4 inches or shorter, all right? 5% probability that that child will grow up to be 65.4 inches or shorter. All right. Do we have any questions about that before I do another one? Can I get a hand raise if you have a question? Okay, so let's have our participation go through the roof on this one. I'm going to go ahead and I'll leave that there. I'll leave that there. What's the probability that you get let out at some point that is 2 minutes after the bell rings? Probability that I let you out at some point that's at least 2 minutes after the bell rings. Actually, I'm sorry, guys. I'm going to change it. I'm going to say at least 1 minute after the bell rings. What's the probability that I let you out at least 1 minute after the bell rings? Oh. All right. Lizette, are you able to talk right now? Remember, your microphone might be muted. All right, that's okay. Connor, can you tell us how you got 0.6?
Sorry, I was doing something real quick.
Oh, okay, no problem. All right. You want to tell us how you got 0.6, Lizette?
Yes, I multiplied 3 times 1/5.
Perfect. All right. Multiplied 3 because it's at any point that's 1 minute after. All right. And so that's actually going to be, all right, it could be 2, 3. All right. So we've got 3 chunks right here from 1 minute after to 2 minutes after, from 2 minutes after to 3 after, and from 3 minutes after to 4 after. So we're going to shade in that part right there. All right, and so what percent of this rectangle is now shaded in red? That's going to be 3 times our height, which is 1/5. All right, and that's equal to 0.6. All right, perfect. All right, now one last one, and then we'll stop going over this. All right, and I'm hoping that here's what I want. Here's I'm going to try this out. We'll see what the response is like. The second that you know what the answer is, go ahead and unmute your mic and just shout it into the speaker. You don't have to shout it, just say it. Okay. What's the probability that I let you out exactly when the bell rings?
Pretty much 0.
Yeah, I was
Pretty
about to say,
much.
wouldn't that be next to 0?
That's correct. All right. It's about 0. We're just going to say 0, although I believe the appropriate way of saying it is approaching 0, because we're going to say that that's an instant, all right, when the bell rings. And so maybe I let you out a second before the bell rings or a nanosecond before the bell rings. In each of those cases, technically, I'm not letting you out right when the bell rings. All right. And so because it's hard to, for an event that's specific to ever happen, we say that the probability of that happening is 0. All right, does anybody have any questions about this before I go over the assignment that was due today or due last class? All right, then let's just go take a quick look at that then. So it says a federal report finds that lie detector tests given to truthful persons have a probability of 0.2 or a 20% probability of suggesting that the person is deceptive. A company asked 12 job applicants about thefts from previous employers using a lie detector to assess their truthfulness. All right. I don't know about you, but if I go in for a job interview and they start strapping me up to a lie detector, I don't know, man. I might hit the door at that point. So they had 12 job applicants. Suppose that all 12 answer truthfully. How many people from a group of 12 honest people are expected to be flagged as liars? Now remember, when we're finding this expected value for binomial variables, it's okay. So what were our numbers? They were 12 times 0.2. Okay, so there were 12 people and 20% of them are expected to be flagged as liars. So that's just going to be 2.4. So that would be our answer on that one. We would just put in 2.4. The second one, it's the exact same scenario, but it wants to know what the standard deviation is. Remember, standard deviation is a measure of variability, a measure of how predictable something is. So if we look at the standard deviation here, remember that, let me go ahead and clear this. To get the standard deviation, we're going to multiply the number of people that we're talking about, which is 12, times the probability that they get flagged as a liar, 0.2, times the probability that they don't get flagged as a liar, which is going to be 0.8. All right, take the square root of all of that, so that's going to be 1.39. So we would have put 1.39 right there. All right, and then lastly, I did get a bunch of questions about this one. Now this is just needing us to use the that binomial equation. Let me go ahead and read the question really quickly. It says, as a special promotion for its 20-ounce bottles of soda, a soft drink company printed a message on the inside of each cap. Some of the caps said, "Try again, sucker," while others said, "You're a winner, baby." The company advertised the promotion with the slogan, 1 in 6 wins a prize. 7 friends each buy a 20-ounce bottle of soda. Can you fill in the missing values from the probability distribution? I'd say round to 4 decimal places here. So I'm going to go ahead and just do this one. All right, so this is asking us what's the probability that 2 of those 7 friends win that get a winning cap. All right, well, what's the probability of winning? The probability of winning is 1 in 6, so we're going to need to use that. So that's our probability of winning is 1 divided by 6, that fraction. 2 of them won in this scenario, so we're going to raise it to the second power, times the probability of getting a losing cap, which is going to be 5 over 6. All right, and there were 7 friends total, so that means that in this scenario, 5 of them are getting the losing cap. All right, times, there's 7 friends total, so we're going to start our multiplication countdown here at 7. All right, but we're only going to go on to include 2 numbers because only 2 friends got a winning cap. And then very important, remember that this denominator here must be in parentheses. So the denominator it was 2 friends, and we're just going to do 2 factorial. So a countdown starting at 2. That would give us a 0.2344 probability. All right. Do you want me to work any of the other ones in that probability distribution?
Could you do the one that was for number 1? Or sorry, yeah, 1 on question 5. That's what I meant.
This one right here?
Yes.
Okay. So we're gonna have 1 divided by 6 raised to the first power, all right, times 5 divided by 6 raised to the 6th power, because there's 7 friends total, so 6 of them got losing caps. All right, times, and here we're just gonna have 7 divided by 1. Let me think. Yep, yeah, that's going to be right. Remember that this whole thing right here is just telling us how many different ways that you could that could happen. All right. So I'm going to do the thing where I try to be a teacher that makes eye contact with his students. So that fraction that comes at the end of that calculation, it's just telling us how many different ways in which that scenario can occur. So how many different ways can you get 1 winner and 6 losers out of that group of 7 friends? Well, there's 7 ways, all right? The first way is that we'll say the oldest friend gets the winning cap, but the rest lose. The second way is that the second oldest friend gets the winning cap, but the rest losing caps. The third way is that the third oldest friend gets the winning cap and the rest get losers, and so on. So the 7 different ways are basically, you know, each way for a way for each one of those friends in which they're the only winner. All right, so let me go back to that. All right, so we'll go ahead and press enter. So we should have gotten 0.3907. All right, here I'm going to go ahead and test my answer key. I kind of always shudder whenever I do this. Okay, yeah, so that we answered that one correctly. All right, do you guys have any other questions? All right, I got one attempt for the bonus response, the bonus question at the end of the video. I don't know. Raise your hand if you want me to solve the bonus question. I feel like I got to hold off on it. I got to hold off until I'm going to go over it next class. Okay, guys. Because I don't know. I'm afraid that if I let the answer slip, then it's going to run like wildfire throughout all the students, because it'll be an incredibly popular thing to talk about. All right. All right. Well, we'll call it a day. You guys have been awesome. I very much appreciate your guys' participation. I'll stay on the line if you have any questions. But if not, then enjoy the rest of your day, and I'll see you guys on Thursday. All right, take it easy, guys.
Bye. Have a nice day.
You too.